Hi everyone, my name is Kuvina and welcome back to another video. Just a disclaimer, this video contains flashing lights. Also, check the description for any corrections or clarifications. So you've probably seen these sorting algorithm visualizations before. They visually represent the array with colorful shapes and show what it looks like after every operation. Sometimes, just watching it do its thing is enough to understand how an algorithm works. But sometimes you can't really tell what's going on. So in this series, I'll be explaining how each algorithm works, accompanied by visuals from a program that I made in C++. So let's get into it. So a sorting algorithm is just a series of steps that the computer uses to reorder the elements of an array such that each one is greater than or equal to the ones before it. To make things simple, we'll use list to refer to the array and piece to mean element. There are two simple methods that immediately come to mind: selection and insertion. With selection sort, you go through the list left to right. For each piece, you find the smallest one from that point onwards and swap it with your current position. This has the effect of putting the smallest piece first, the second smallest second, the third smallest third, and so on, which means once you reach the end, the list will be sorted. To find the smallest, you have to look through the entire unsorted section. This involves a lot of read operations, which are visualized by turning that piece white. There's a pretty simple improvement called double selection sort. This time, you have two current positions, A and B. A goes left to right, and B goes right to left. Every round, you find both the smallest and the largest piece from A to B. Swap the smallest with A and the largest with B, and repeat. Double selection does half as many rounds as single selection, making it twice as fast. Now let's look at insertion sort. Again, you go through the list left to right. For each piece, assume the ones to the left are already in order. Now you find the place where the current piece belongs within that sublist. Then, starting in the old location, shift pieces to the right until there's an opening at the destination and put the piece there. The reason you can assume the previous pieces are in order is that the size of the sorted sublist increases every round. Insertion sort has way more write operations than selection, but when you factor in read operations, they're pretty comparable. In regular insertion sort, you have to go through the whole sorted sublist, making comparisons until you find the destination. But binary insertion makes this process faster using binary search. You start by checking the midpoint. If your value is greater, then it goes in the right half, and if it's smaller, it goes in the left half. You can continue checking the midpoint on whatever half you end up with, and eventually you'll find the exact destination. This effectively cuts your search space in half every check, which means for a sublist of size x, you only have to do log base 2 of x checks rather than x over 2 on average with regular insertion. Unfortunately though, you do still have to shift the pieces over one by one. Now selection and insertion are both pretty straightforward in concept. An algorithm that I believe is a bit more creative is Bogo Sort. For each round, you go through the list left to right looking at each adjacent pair. If the first piece is bigger than the second one, then you swap them. When you reach the end, the round is done. You keep doing rounds until the list is sorted. You know the list is sorted if you haven't made any swaps that round. Upon implementing this, you'll notice that after round x, the x largest pieces will be sorted at the end, so you can actually skip them to avoid unnecessary checks. Bogo Sort has a small improvement as well, called shaker sort. Instead of always going left to right, it alternates direction. This way, it carries the biggest pieces to the end and the smallest ones to the beginning. But in practice, it's only slightly faster than Bogo Sort. So far, these algorithms have been fast and easy to write code for, but they haven't been very fast at sorting. To see why, you need to know something called asymptotic notation. If f and g are both functions, we say that f of x is in O of g of x if it's possible to scale f by some constant a in a way that a times f of x is always less than g of x past a certain point. For example, consider g of x equals x and f of x equals 10 log base 2 of x. Even though f of x starts off bigger, it will eventually fall behind due to the shape of the logarithm graph, so f of x is in O of g of x. What about g of x equals x squared and f of x equals 4x squared plus 400. This is where the scaling comes in. F of x will never be less than g of x, but 0.2 times f of x will be at some point, meaning f of x is an O of g of x. In general, you can ignore everything but the leading term in polynomials. Coefficients don't matter, and the bases of logarithms don't matter either, since changing that just scales by a constant anyway. Instead of thinking of this definition every time, we can think in terms of subsets. O of 1 is a subset of O of log x, which is a subset of O of x, which is a subset of O of x log x, which is a subset of O of x squared, and so on. All of these are in O of 2 to the x, which itself is a subset of O of x factorial. Now, how does this apply to sorting algorithms? Well, if n is the length of the list, then we can say f of n is the number of operations that the algorithm performs while sorting. These operations include both writing values to the list and reading values from the list. Since both of those take non-zero time for the computer to do, f of n also relates to the time complexity of the algorithm. This is where those subsets come in. Technically, if f of n is in one of these, it's also in all of the larger ones, but we're only concerned with the smallest one it's in. So if an algorithm has an operation count within O of n squared, but not in O of n log n, we would call this a time complexity n squared algorithm. Now suppose you have two algorithms, A and B. If A is n log n and B is n squared, then does that mean A is always better than B? No, but it does mean there will always be some number big N where A is faster than B for any input size greater than big N. A final note about time complexity is that the number of operations can vary depending on the exact input. Each algorithm has an average time complexity, but it may have a different best case or worst case time complexity. There are several ways to find the time complexity of an algorithm. One way is to go through the pseudocode step by step and count the operations. With insertion sort, there are n-1 rounds, so these get called O of n times. There's a nested loop with as many sub-rounds as necessary to insert the piece. On average, that's x over 2, where x is the round number, so these are called O of x times per round, or O of nx times total. X varies by round, but the mean value is n over 2, which is an O of n. That means these operations are called O of n squared times, more than anything else in this algorithm, so insertion sort is n squared on average. In the worst case, you'll have to insert at the beginning every time, which doubles the number of sub-rounds, but that doesn't change anything, so the worst case is still n squared. In the best case though, there's only one sub-round per round, which results in total operations in O of n. We can use the same reasoning to get time complexity for binary insertion, selection, and double selection. For Bogo Sort, we can actually find it in a really interesting way. So each piece will have a starting position and an ending position. The mean distance between these is 1/3 of n. Bogo Sort moves pieces only one spot at a time, so on average it will take at least that many operations to get a piece to its destination. That's in O of n, and there are n pieces, so it's O of n squared total operations, making Bogo Sort n squared on average. So although each algorithm has distinct advantages, they've all been n squared on average. We can get down to n log n using a strategy called divide and conquer. Essentially, you can divide a problem into multiple sub-problems. This might require additional steps, but often the sub-problems are so much easier than the main problem that it's faster to do it this way. There are two main divide and conquer algorithms, quicksort and merge sort. We'll start with quicksort. The idea behind quicksort is to partition the list into two sublists where each piece in the first is less than or equal to each piece in the second. Then, by sorting each half, the full list will automatically be sorted. The partitioning step is done as follows. First, you set a value called the pivot equal to the first value in the list. Then you keep track of two positions, A and B. A moves left to right until it finds a piece bigger than the pivot. B moves right to left until it finds a piece smaller than the pivot. Once both of these are found, you simply switch A and B and repeat. Eventually, A and B will meet up. When this happens, you place the pivot right before their meeting location. Now sort everything to the left of the pivot, then everything to the right of it separately. What algorithm should you use though? Well, you can actually just do quicksort again. That's right, quicksort is a recursive algorithm, meaning it calls itself. You just need a condition so that it doesn't do anything with a list size less than 2, and then you have a working algorithm. Now, what's the time complexity? Well, partitioning a list of size x is O of x because you read each piece at most once and swap each piece at most once. How many times is it called though? Well, ideally, the list would get split in half, but depending on the pivot, you can get lopsided sublists. On average, you'll get 3/4 and 1/4. The deepest level of recursion will be if you follow the larger sublist every time. That results in log base 4/3 of n total recursion levels, which is in O of log n. The total length at each level is at most n. As a result, quicksort is n log n on average. In the best case, it gets split in half every time, but that's still n log n. In the worst case though, you can actually have n recursion levels, making it n squared. Now on to merge sort. It starts by splitting the list right down the middle, and then sorting each half separately. Then it's really easy to combine the halves, since each one is sorted already. The combining step is done as follows. First, you need an auxiliary array. This is an extra array that you can delete after this step. Now you know each half is already sorted, so you're going to have 2 current locations, A and B, starting at the start of each half. Now whichever one is smaller, you add that to the auxiliary array and move that current position over by 1. You keep repeating this until one of the halves is done, and then you fill in the rest with the other half. Now you copy that onto the original array, and you can delete the auxiliary array. Like quicksort, merge sort is recursive, so you have to make sure it stops once the sublist gets small enough. The combining step is O of x with sublist length x, so merge sort has time complexity n log n for the same reasons we saw before. But unlike quicksort, merge sort cuts the list in half every time, so there is no worst case. Merge sort may have the better worst case, but quicksort is still faster on average. Merge sort has another advantage though. It's a stable sorting algorithm. This means that if you have multiple pieces with the same value, then whatever order they're in before, they will stay in that order after sorting. The reason it's stable is if you're merging the 2 halves and you encounter a tie, you can just prioritize the left one. But why would you care about something like this? Well, often you need to sort by multiple things at a time. For example, sorting cities primarily by country name, and within each country by city name. You'd think you might have to sort by city name 4 separate times, but with a stable algorithm, you can simply sort the whole list by city name, and then sort it again by country name, and it will have this property. With an unstable algorithm though, you'll probably lose that property as soon as you sort by something else. Merge sort is stable, but quicksort isn't. And looking back on the other ones, insertion and Bogo Sort are stable, but selection sort is not. Another thing to consider is space complexity. Just like how time complexity relates to operation count, space complexity relates to how much extra memory you need, not counting the original list. The n-squared algorithms have all been O of 1 space complexity. That's because swapping pieces one at a time only needs one temporary variable. But merge sort uses auxiliary arrays. The biggest combining step is the final one, which needs an auxiliary array of size n, which is of course in O of n. Quicksort doesn't use auxiliary arrays, so you'd think it's also O of 1, but it's actually O of log n due to recursion. Every time the algorithm enters a new recursion level, it has to remember where it left off in the previous levels, which takes up space in memory. Since quicksort has O of log n recursion levels on average, that's also going to be its space complexity. You'll notice that usually the faster an algorithm is, the more space complexity it will have. This is something called space-time trade-off, and it's actually a really universal concept and applies to a lot more things than just algorithms. Once you know about it, you'll start to notice it everywhere. My favorite example is in special relativity, where when you move faster through space, time dilation makes you move slower through time, and if you're interested, I have a whole video about time dilation. Anyway, now that we've incorporated stability and space complexity, we can see that even the n-squared algorithms do still have advantages. So that raises the question, is it possible to improve these algorithms but still maintain these advantages? The answer is yes. We'll start with Selection Sort, which has an improvement called Heap Sort. The main issue with Selection Sort is that to find the min, you go through the entire unsorted sublist every single time, which is O of x. We can fix this with a data structure called a max heap. That's just a binary tree where each node is greater than or equal to each of its two children. Also, it must have the property that you can read through it left to right, top down without any gaps. When you do that, the pieces aren't necessarily in order, but the biggest one is always first. You can extract the max by removing it and replacing it with the last piece. It will no longer be a max heap anymore, but you can make it a max heap again by simply moving that piece down, switching with whichever one of its children is larger until you have a max heap again. With x pieces, there will be log base 2 of x layers, meaning extracting the max is O of log x. If you repeatedly extract the max and put them in reverse order, then this sorts the max heap in n log n time. But to use this as a sorting algorithm, you first have to convert your data into a max heap. That can actually be done without any additional memory by making clever use of the original array. If you store the values of a max heap as an array where the indices go left to right, top down, you might notice something. For each piece, if the index is I, its left child has an index 2i plus 1, and its right child 2i plus 2. So any array is already a binary tree if you just use the indices like this. Now that process from earlier of repeatedly moving a piece down has a name. It's called max heapify. If each child is already the start of a max heap, then index I will be as well after this step. So to turn the original array into a max heap, you just do this for every piece in reverse order. Actually, you only do this with the pieces that actually have children, which is only the first half of them. Since we're using the original array, you extract the max by switching it with the last piece and taking it out of commission by decreasing a variable called length. So the final algorithm starts by building a max heap, and then it repeatedly extracts the max n times. Since max heapify is log n, it means build max heap is n log n, extract max is log n, and finally heap sort itself is n log n. And unlike merge sort or quick sort, it only has space complexity of 1. Now let's improve bubble sort. Its main issue is that it only moves pieces one space at a time. There's actually a really simple fix for this called comb sort. Instead of checking adjacent pairs, you check pairs with certain gap size. The gap size can start off large and then gradually shrink until it's size 1. That way, you get the big changes out of the way first, so that all you have left are minor adjustments. And if it's not sorted after gap size 1, then you can just repeat that round until it is sorted. To find a sequence of gap sizes, you can just start with n and continually divide by a number called the shrink factor. The optimal value can be found through trial and error, and it's about 1.3. The time complexity is worse than n log n, but it's actually better than n squared. You can experimentally find the time complexity by graphing input size versus operation count. If you use a log-log plot, then a straight line means you have a power function, and the slope is the power. Sure enough, doing this with the n squared algorithms gives a slope of 2. But with comb sort, you get a slope of around 1.2, so its time complexity is about n to the power of 1.2. Now let's improve insertion sort. Its main issue is that shifting everything over takes a long time, but if the list is already roughly sorted, then you don't have to shift over very much. The algorithm that takes advantage of this is called shell sort, and it performs several rounds of gapped insertion sort. Gapped insertion works as follows. With gap size k, you go through the list left to right. For each piece, you only consider pieces multiples of k to the left of it, and then insert the current piece wherever it belongs among those. When you've gone through the whole list, every sequence of pieces spaced k apart will be internally sorted. We call this property being k-sorted, and although it doesn't guarantee the list is sorted, it will be roughly sorted, making insertion easier. Now, just like comb sort, you repeatedly divide by the shrink factor to get gap size for gapped insertion. Unlike comb sort though, you never need additional rounds with gap size 1 since that's just regular insertion sort and is guaranteed to sort the list. The optimal shrink factor is again found by trial and error, and this time it's actually around 2.3. I found the time complexity to be about the same as comb sort, n to the 1.2, but I also found shell sort to be about twice as fast. All of these algorithms so far have been comparison-based, which means they figure out where pieces go by comparing them to other pieces. This allows them to sort not only numbers, but any object that has some kind of comparison operation. This can be custom variable types or even class objects. With comparison-based algorithms, it's mathematically proven that you can't get better than n log n average time complexity. With non-comparison algorithms, you can get down to n, but it requires you to make some assumptions about the data. Also, these algorithms typically only sort numbers. The main type of non-comparison sort is Radix Sort. It involves looking at the individual digits of the numbers, and as a result, it can only sort numbers. The digits depend on what base you use, so instead of base 10, computers usually do better with powers of 2, but we can use any base b. Now here's the basic concept behind Radix Sort. So if you remember, you can use a stable algorithm to sort by multiple things. For example, sorting the entire list by city name, and then again by country name, makes a list sorted primarily by country name and secondarily by city name. The same thing applies to numbers. If you add leading zeros and look at the digits of a sorted list of numbers, they're sorted primarily by the first digit and secondarily by the second. So with a stable algorithm, you can sort each digit in reverse order, and that will sort the whole list. This is easier to visualize in binary base 2. Now here's how you sort by a specific digit. First, go through the list and copy each piece to an auxiliary array. At the same time, make note of the digit in question for each piece and count how many there are for each possibility. A prefix sum of this tells you exactly where each digit group should start. For each one, you'll have some current position to keep track of. Now go through the auxiliary array, add each piece at the correct current position, and increase it by 1. Now the list is sorted by that particular digit, so you just repeat for all the remaining digits in reverse order, and your list will be fully sorted. So what are the time and space complexities of Radix Sort? Well, it actually depends on a lot of things, not just n. Sorting by digit uses additional arrays of size n and b, and going through those takes time, so its space and time complexities are both O of n plus b. This is deleted every round, so full Radix Sort has the same space complexity, but for time complexity, you multiply it by the number of rounds. This is just the number of digits in the maximum number, which we'll call d. Time complexity is O of d times n plus b. The logarithm function actually works as a digit counting function, so if r is your max value, then d equals log base b of r, and we can substitute that in. Now, if we assume we're using a constant base b regardless of n, then these simplify to O of n times d and O of n log r. If you know you're never going to have pieces bigger than a particular value, then r is constant, so it's in O of 1, which means n log r simply becomes n. But if your range of potential values scales proportional to n, then r is in O of n, meaning n log r is n log n. This is actually the same case if r is proportional to some power of n, since powers within logarithms become constants. But if r is exponential compared to n, you actually get n squared. So the time complexity is heavily dependent on the maximum value. Often, you just don't know what that's going to be, so radix sort can be unpredictable. This type of radix sort is called least significant digit because you go through the digits in reverse order. But there's another variety called MSD where you go in the straightforward order. Doing it this way requires you to sort each section separately, which makes it recursive. This recursion makes it more complicated to write code for, and it also adds time and space complexity, so MSD is usually the inferior type of radix sort. It does have one advantage though. You can modify MSD radix sort to add trailing zeros instead of leading zeros. This basically sorts in alphabetical order, which works on words because they're essentially just base 26 numbers. Similar to MSD radix sort is bucket sort. It basically sorts the list into a finite number of sublists called buckets, and then sorts each bucket using whatever algorithm you choose. This is similar to radix sort, but the buckets aren't necessarily based on digit. You can manually define the buckets ahead of time, but usually you need to adjust based on the input. If each bucket covers an equally sized range of numbers x, then you can determine a given piece's destination by dividing its value by x. If r is your max value and b is number of buckets, then you can use x equals r over b, and your buckets will cover the entire range of values. Relying on division for the bucketing step makes this a non-comparison algorithm, and it can only sort numbers. For the purposes of this video, we're going to say the bucketing step uses the same technique as radix sort with the auxiliary array and counting the pieces. Also, we'll use insertion sort for each bucket, since that works well on small sublists. Now, you might wonder, what would happen if we sort each bucket recursively? Well, that's effectively just a weird version of MSD Radix Sort. The bucketing step has n plus b time and space complexity for the same reasons we saw in Radix Sort. If s is the length of a given bucket, then sorting it with insertion sort is s squared time complexity. The thing is, we don't know how big each bucket will be. Depending on your input, you can get way more values in a single bucket. But if we assume a uniform distribution, then the length of each bucket is about n over b, so each insertion step is n squared over b squared. There are b rounds of this, so the insertion step in total is n squared over b. Adding in the bucketing step, we get time complexity n plus b plus n squared over b. Is this good? Well, it depends on your choice of b. If b is constant, then it's just going to be n squared. That's because, for example, doing insertion sort on 1/10 of a list 10 times is 10 times faster than if you did insertion on the whole list, but this 1/10 is regardless of the input size, meaning it's a constant scaling factor that doesn't change time complexity. But if you make the number of buckets proportional to input size, then bucket sort actually becomes linear, since now each bucket has a constant size regardless of n, so insertion is O of b, which is the same thing as O of n. So that's pretty cool how by assuming the input is uniformly distributed numbers, we can get linear time. But if that's not the case, you can get a large bucket, and sorting that takes a long time. There's a way to get around this though. If you make each bucket have such a small range that only one value belongs in it, then you don't even need to sort each one. Then the bucketing step is the entire algorithm. This is called counting sort. If you're using floating point numbers, you'll need billions of buckets, so it only works with integers. Basically, you find the maximum value r and make a bucket for every possible integer value up to r. Then you do bucket sort as normal, but skip the step of sorting each bucket because you will already be done. This is pretty much just radix sort with base b equals r. Log base r of r is 1, so time and space complexity are both n plus r. We can compare this time complexity to radix sort with a fixed base. If r is an O of 1, it's a tie. If r is an O of n, counting sort wins. If r is O of n squared or more, radix sort wins. And counting sort can even get exponential. So counting sort is pretty good if you have a lot of values in a small range. Now let's look at some impractical sorts. When I say impractical, I don't mean they're necessarily bad at sorting, it's just not practical to implement them to sort an array on the computer. The first of these is spaghetti sort. If you have a bunch of uncooked spaghetti, you can find the longest one really easily with the following method. First, make them into a bundle and let them fall to the table. Then the longest one will just be the first one you encounter from the top. Now you can repeatedly extract the longest and put it at the end of a list. This is effectively a selection sort that runs in O of n time. This works well in the physical world, but in the digital world, you can't do this unless you have n parallel processors, and in that case, there are much better algorithms. Then there's gravity sort. If you're given a list of integers, then you can represent them as a series of stacks of squares. Then you can convert these squares to beads on horizontal bars where each one can move freely left to right. In that case, all you have to do to sort them is shift everything to the right. You can even make use of gravity by tilting the entire setup. You can replicate this in the digital world as follows. If n is the list size and r is the maximum value, then you represent the beads with an n by r Boolean array. Now, you could shift the beads over one by one, which makes a nice visualization, but there's a faster way. All you have to do is count the number of beads in each row and overwrite each row with that many ones on the right side and the rest of the row filled in with zeros. After doing this for every row, you just have to count the number in each column to get the sorted list. If r is the max value, then the time and space complexity are both O of n times r. Depending on r, time complexity can actually be linear, but no matter what, space complexity is still really bad. Gravity sort can only sort integers, and it can't even sort multivariable objects by a specific value, since it doesn't actually shift the objects around, it just changes each one's value. So gravity sort is not very practical, but it is very cool. Another one just like that is Pancake Sort. Imagine you have a stack of pancakes, each of which has some associated value. You can't just move pieces around freely. Instead, your only way to move them is picking up the entire stack above some point and flipping it. This is equivalent to a bunch of symmetrical swaps. There is one really simple way to sort this, which is basically just selection sort. You find the minimum and then flip the stack to make it be on top. Then you flip the stack again to put that piece exactly where it needs to go. Implementing this on the computer gives time complexity n squared, and it's just like selection sort but with a bunch of unnecessary swaps. However, if you count the number of flips rather than the number of operations, it actually relates to a really interesting unsolved mathematical problem of finding the minimum number of flips. The algorithm just described can sort any stack in 2n-3 flips, but it's possible to do fewer. The minimum number is unknown, but it's proven to be within 15/14 of n and 18/11 of n. And then there are even joke sorting algorithms. No, not algorithms that sort jokes, algorithms that are jokes. The most famous of these is Bogo Sort, which works as follows. First, check whether the list is already sorted. If yes, then you're done. If no, then randomize the list and check again. Keep repeating until the list is hopefully sorted. Bogo Sort is unique because it's not guaranteed to sort the list in finite time, meaning the worst case time complexity is literally infinite. In the best case though, you just have to check the list once, so the best case is linear. So if the best case is really good, and the worst case is really bad, then is the average case any good? Not even close. The chance of the list being sorted is 1 in n factorial, so that's the expected number of rounds. Randomizing and checking are both O of n, so average time complexity is n times n factorial. Not only is this worse than n squared, it's worse than any polynomial, and it's even worse than any exponential. Anyway, that concludes part 1. The algorithms that I've covered so far are what I believe to be the most important to understand, and all remaining algorithms reuse these same concepts. But since the series is called Explaining Every Sorting Algorithm, there's still a lot more to talk about. But this video is already really long, so those algorithms will be in part 2. I plan on covering all of these that you see on screen right now, but if you know of any really obscure algorithms that I might miss, let me know in the comments. With that, we've reached the end. Make sure to like and subscribe. Of course, you don't have to, but at least think about it and really consider whether you want to. Also, I recently made a Twitter account at Kuvina_4, so I recommend you go follow me on there. Thank you for watching, and I hope to see you again soon in part 2. Bye!